Is the screen visible? Hello.
Yes, sir.
Okay. So we had started with pharmaceutical analysis. Okay. We will just revise what we have seen till now and then we'll see for today's part. So in pharmaceutical analysis, we were seeing the titrations part, which is one of the important topic in for your GPAT examination. So first we saw the fundamentals of volumetric analysis, in which what are the basic prerequisites or pre-requirements to conduct a volumetric analysis. What is a volumetric analysis? Doing the analysis with the help of like doing analysis of unknown concentration with the help of a known concentration solution. Okay, that is a volumetric analysis. And to perform a volumetric analysis, what are the basic requirements that we study? And from these basic requirements, we come to know that how we would be going to perform the volumetric analysis and what are its fundamentals. So when we are talking about classification of volumetric methods of analysis, volumetric methods of analysis is divided into five major classes, okay, or five different types of volumetric analysis we perform. The first is aqueous acid-base titration, the next is non-aqueous titration, next third is precipitation titration, fourth is complexometric titrations, and fifth is redox titrations. Now these all five types are just described in brief here. Okay, so aqueous acid base titration or neutralization titration, it involves neutralization reaction in presence of water as solvent. Non-aqueous titration, solvent is other than water, that is that they can be organic solvents. Precipitation reactions, you know, so the titration which involve precipitation reaction is the precipitation titration. Okay, so one of the example of precipitation reaction is also given here. Next is complexometric titration, in which complex formation uh, is the basic fundamental involved, and EDTA titrations also they are known as, because EDTA is mainly used as a complexing agent. Then we have redox titration. Now, as the name suggests, redox titrations means where a simultaneous oxidation and reduction reaction occur. Okay, so in those reactions are applied in this titration, so we call them as a redox titrations. So out of these, we have completed the acid-base titration, non-aqueous titration, precipitation titration, complexometric titration. We will be going to see redox titrations today. Methods of expressing concentration. So there are different methods to express concentration. Here we have normality, okay, that we had studied. Then we have percent concentration, molar concentration, and molar concentration. So for normality, when we just a minute, okay, normality, what is the definition? The normality of a solution is defined as number of gram equivalent present per liter of the solution. Okay, number of grams equivalent present in a liter of solution is normality. Okay, the next percent concentration, that is concentration is many a times expressed in time. Okay, percent concentration is just percentage. Molar concentration, we have the definition. Molality of the solution is given by the number of moles of solute per kg of solvent. Okay, number of moles of solute per kg of solvent is molar concentration, and normality is gram equivalent per liter of solution. And next we have molar concentration. Okay, number of moles of solute per liter of solution. Next is primary and secondary standards. What are primary standards and what are secondary standards? We understood that. So primary standard is a standard substance, okay, which is accurately known. Okay, each and every property of it we have known accurately. And secondary standards are the substances which we have standardized with the help of primary standard as a reference. Okay, those are secondary standards. These are the properties of primary standard substances mentioned here. Also, few examples of primary standards are mentioned. We had already studied this. Secondary standard substances, we have studied. Here are few examples. What is secondary standard? Which is standardized with the help of a primary standard. We call that as a secondary standard substance. Important definitions and terms. It is one of the important point here. Okay. So volumetric or titrimetric analysis, standard solution, titrate or titrant, equivalence point or stoichiometric endpoint, indicator, titration error. Okay, these are important definitions. True value, standard value, and observed value. We have covered this part as well. Then we had started with acid base titrations. Okay, aqueous acid base titrations. So before studying the titrations, we had studied acid base concepts and different theories proposed by different scientists, like the Arrhenius theory, Bronsted Lowry theory, Lewis theory we had studied. Okay, and the summary of all these theories is mentioned here. The next we studied the solvents involved in these acid-base aqueous titration. So polar protic solvents and polar aprotic solvents are mentioned here, but our polar protic solvent are used in aqueous acid-base titration. Okay, that is the water, which is a polar protic solvent, which is used here. Next, definitions of strong acid and base, weak acid and weak base, and buffer solution. Also, their examples are given here. Okay. Next, we studied common ion effect. So, common ion effect is one of the important point when we study the acid base titrations. Okay, and the basic law behind the common ion effect is the law of mass action. Next, we studied the indicators used in aqueous acid base titration. Different indicators which we can use in different pH range are mentioned, and also the color of these indicators, like from which pH to which pH, whenever they are getting changed, how the color varies. Okay. Next, we have some indicators with their pH range, or like if we are having a strong acid and strong base titration, which indicator we can use, like based on the different titration, which indicator we can choose is mentioned here. Okay. Next is mixed indicators. Mixed indicator is like we mix one or two or more indicators to get the exact accurate results. Next, theories of indicator. In theories of indicator, there are two theories of acid base indicator. First is Oswald's theory and second is quinonoid theory. Hello, hello, am I audible?
Yes, sir.
Yes, okay, 1 minute. Sorry, there was some network issue. So in theories of indicator, we had studied two theories of indicator, Oswald's theory and quinonoid theory. Okay, 1 minute, huh? Just there is some network issue at my end. Just a minute. Yeah, am I audible now? मेरा आवाज आ रहा है सबको?
Yes, sir.
Okay, okay, thank you so much. Yeah, so we had studied Oswald's theory, okay, under theories of indicator, and another theory that we studied was the quinonoid theory. We had already discussed both of these theories. Then we studied titration curves, okay. Titration curve, when it is a acid base titration curve, we call it as a neutralization curve. So we saw different titrations, like a strong acid and a strong base titration, and we studied the titration curve of this titration, okay, in detail. Then titration of a weak acid and strong base and its curve we studied in detail. Titration of a strong acid and a weak base, and titration of a weak acid and a weak base. We also summarized all this data. Then we studied non-aqueous titrations. In non-aqueous titration, we studied why there is a need of non-aqueous titration and what are the different examples of non-aqueous titration, okay, need of non-aqueous titration, and what are the other solvents used in non-aqueous titration. So protogenic, protophilic, protic and amphiprotic solvents, okay. Then titrants used in non-aqueous titration. So acidic titrants and basic titrants are enlisted here, few examples. Next, we studied complexometric titrations. So, complexometric titrations, we studied what are complexometric titration, principle behind complexometric titration, okay, how is the complexation taking place, and how the indicator is working, okay, the change in the color of the indicator, okay. So, this is very important. Then complexing agent, we studied different complexing agent, in which we first studied EDTA, that is ethylene diamine tetraacetic acid, DTPA diethylene tetramine pentaacetic acid, EGTA ethylene glycol bis amino ethyl ether tetraacetic acid. Then we studied masking and demasking agents. Masking and demasking agents are important when we need to estimate multiple metal ions, okay, in a solution, or we need to estimate one, but we do not want hindrance of other metal ions, so we use masking and demasking fundamenta here. So different kind of masking we can perform by masking by complex formation. So if we are using that, what different kind of complexes we can form, that is enlisted here, and different kind of masking agents also. Then demasking, how we will perform and what are demasking agents, or how we can do the demasking thing. So complexometric titration can be performed like in direct way, back titration replacement, and indirect titration way. So how we will perform direct titration, back titration, replacement titration, and indirect titration, we had discussed already. Then indicators in this complexometric titration. So here are the indicators that we use in complexometric titrations. Instrumental methods for endpoint detection. So these are different instrumental methods by which we can detect endpoint, like in complexometric titration or different titrations we can use these instrumental methods. Then we studied in the last lecture precipitation titration. So precipitation titration, where precipitate formation is considered as the end point of the reaction. Okay, so this is the basic fundamental behind the precipitation reactions or precipitation titrations. Uh, then we studied different fundamentals behind precipitation titration, and then effect of solubility of precipitate, like different conditions like acid, temperature, solvent, how is the solubility of precipitate, that we studied. Then we studied argentometric titrations, okay, where silver nitrate is used as a precipitating agent, we call them as argentometric titration. This is the plot for argentometric titration. Then titration involving ammonia and potassium thiocyanate, that we call it as thiocyanometry. Okay, this we studied. Then mercurometry we studied. Then Gay-Lussac's method, Morse method, and Vollard method we studied. Fajan's method we studied. Now for today's session we'll be studying redox titration. Redox titrations are also known as oxidation reduction titrations. Okay. So oxidation reduction titrations, you all are aware of oxidation reduction reactions, okay? The same fundamental is applied here in the redox titration, that is oxidation reduction titration. So concept of oxidation and reduction, first we'll see that. So redox titration, a titration which deals with a reaction involving oxidation and reduction of certain chemical species, okay? Of a certain chemical species, if there is a oxidation and reduction going on, and if we are using this reaction as a titration, then we call it as a redox titration. Titration, the act of adding standard solution in small quantities to the test solution till the reaction is complete, is termed as titration. Titration means what? Again, the definition I have mentioned here, that what is a titration? Titration means in which we add standard solution drop by drop into the test solution until the reaction is complete. We call this process as titration. In this process, if there is oxidation and reduction involved, we call that as redox titration. A standard solution is one whose concentration is precisely known, and test solution is the one whose concentration is to be estimated, okay, or test solution we can call it as unknown solution. Next, oxidation and reduction, okay. So reaction, the old definition of oxidation is combination of substance with oxygen. We call it as it is a oxidation reduction, like oxidation reaction. Like if carbon combines with oxygen and forms carbon dioxide, we call it as oxidation reduction. This is a old definition of oxidation reaction. The current definition of your oxidation reaction is loss of electrons is oxidation. Okay, LEO, oxidation. This is the easiest way you can keep in mind. LEO means oxidation. Okay, that is loss of electron. Okay, is oxidation, loss electron, oxidation. Like you can see here, sodium, when it loses electron it gets oxidized. Okay, positive charge represents electron deficiency. One positive charge means deficient by one electron. Okay, so this positive charge means this sodium has got oxidized. Reduction reaction, old definition, removal of hydrogen from a compound. Okay, like we have removed hydrogen from this compound, so we call it as a reduction reaction. Or we had added hydrogen to this compound, we can call it as a reduction reaction. Current definition, which is now widely accepted for the reduction reaction, is gain of electrons is reduction reaction. So GER, gain of electron is reduction, loss of electron is oxidation. Okay, so chlorine is gaining electron. Okay, and it is gaining a negative charge after accepting the electron. So negative charge represents electron richness. One negative charge means rich by one electron. So this chlorine had got reduced by gaining one electron. Okay, and now this chlorine is electron rich because it has one extra electron with it. Redox reactions, oxidation and reduction go hand in hand. In a reaction, if there is an atom undergoing oxidation, there is probably another atom undergoing reduction reaction. Most of the times oxidation and reduction reactions go simultaneously or in hand. Okay, so when there is a substance who is undergoing oxidation, there would be most probably a substance who would be undergoing reduction reaction. Okay, then when there is an atom that donates electron, there is always an atom that accepts electron. If someone is donating, there should be someone to accept the electron. So when there is oxidation, there is always reduction, and these both reactions go hand in hand. Electron transfer happens from one atom to another. Okay, electron transfer happens, and thus redox reactions takes place. Theory of redox reaction. So titrations, redox titrations usually make use of highly sensitive electrolytic cell that essentially consists of two different types and typically uses electrodes such as indicator electrode and reference electrode. So in redox reactions or redox titration, we use electrolytic cells. Now this comes into your electrochemistry that you have studied in your 11th 12th. Okay, so in which we use two different electrodes. Okay, for conduction of that reaction. So these two electrodes would be, one would be an indicator electrode and another would be a reference electrode. Indicator electrode, it consists of a noble metal. Okay, what is an indicator electrode? Indicator electrode is made up of noble metal which simply act as a vitally important center for electron transfer from bulk of solution to the prevailing external circuit. Generally platinum electrode is used for this purpose. Okay, reference electrode are standard hydrogen electrode and standard calomel electrode. You have studied these. Okay, so just names are sufficient. Standard hydrogen electrode SHE and standard calomel electrode SCE. Example of titration, titration of iron with Ce. What is Ce? You know, Ce element.
Cerium.
Okay, good. Cerium and iron we are going to titrate in 1 molar HNO3 solution. HNO3 means HNO3. Hello.
Nitrous oxide. Nitrous oxide.
HNO3 is
Nitrous hydroxide.
it correct? What we call HNO3?
Nitrous oxide.
Nitrous oxide.
Nitric acid.
Huh?
Nitric acid.
Nitrous oxide or nitric acid?
Sir, nitric acid.
Nitrous oxide means N2O. HNO3 is nitric acid. Array, you are in third and final year B.Pharm and you don't know HNO3. HNO3 nitric acid. Who was that nitrous oxide? Okay, leave it. The various half reactions are given below. So like iron will donate electron and cerium is accepting electron. So here oxidation is going to happen and here reduction is happening. Okay. So this is the reaction, but from GPAT point of view, we are not going into these details. Redox indicators. So for this redox reaction, we have different indicators. A redox indicator should be such that it produces a sudden change in the electrode potential in the vicinity of the equivalence point during a redox titration. So the redox indicator is actually an electrode and that electrode should show a sudden change in the electrode potential so that we can capture it as the oxidation reduction or the electron transfer has been completed. This is possible when the indicator itself is redox active, that is capable of undergoing oxidation or reduction process which is a reversible one. The oxidized and reduced form of the indicator should have a contrast difference in the colors. Okay, so there should be a difference in the colors also so that we can easily visually see the change. Okay, and we can detect the endpoint. So this is something that is the Nernst equation that you have studied in your chemistry. Okay, 10+2 chemistry. So Nernst equation is given here and the whatever, like what stands for what is mentioned here. So this you can read out Nernst equation, and these mostly it is not asked in GPAT, but few things you should be knowing, like R is the universal gas constant and the value of R is 8.314. Okay, joule per molar per kilomolar. Okay, then F is the Faraday constant and number of coulombs per mole of electrons, F equals to 9.64. So these all you have studied already and you can just revise it out. Okay, not much has been asked on this. Then types of indicators in this redox titration. So we have self indicator, external indicator. Okay, what we'll do now,
Yes, sir.
okay, so we are now going to study types of indicators used in redox titration. Okay, we are studying redox titrations, and under that we are studying the types of indicators. So first is self indicator. So potassium permanganate is one of the best example of self indicator under this category. Many a times the titrant itself may be so strongly colored that after the equivalence point a single drop of titrant will impart a definite pink color at the end point of the titration. So potassium permanganate itself can be used as a titrant and also as an indicator. Okay, so it is a self indicator. Okay, Ceric sulfate, pale yellow, and iodine brown are other examples of this category. The only disadvantage of self indicator is that a slight over titration always occurs. Okay, so this is the disadvantage of self indicator. Self indicator means what? Titrant itself. Okay, titrant itself, it is a indicator. Okay, so we don't need to add any different indicator in the titration. Next is external indicator. External indicator, that is we are going to externally add the indicator. They are based on some visible reaction of the titrated substances with a suitable reagent so that the endpoint is marked by failure to elicit the reaction, or we can mark up the endpoint easily. Okay, in simple terms, potassium ferricyanide, the titration of ferrous ion by K2Cr2O7, drops of solution removed to a spotting tile during titration will give a deep Persian blue color with potassium ferricyanide because ferrous ions are still present. At the end, ferric ions are present and this does not give a color with potassium ferricyanide. So potassium ferricyanide is one of the example of your external indicator here. Internal or redox indicator. Okay, now internal indicator is which we are going to mix with the reaction. Okay, Redox indicators are substances which have different colors in their oxidized and reduced form. The reaction is reversible. Most of the redox indicators are dyes, the reduced form of which are colorless. Okay, so reduced form of these dyes are colorless, but when they are in oxidized form, they gain some color. Like here are the examples: diphenylamine, diphenylamine sulfonate, diphenylbenzidine, methylene blue, and starch. Okay, and color change is given. All of these are colorless when they are in their reduced form, and when they get oxidized, they turn into blue, reddish violet, blue, and blue. Okay, so mostly blue color is the endpoint seen in this redox titrations. Next, we have potentiometric method for endpoint detection. This is the physicochemical method which may be applied not only to those cases where suitable indicators are not available, but okay, but also uh, to those cases in which the visual indicator method fails or has limited accuracy. So when these chemical dyes or these indicators are not giving accurate result, or they are not available, or they cannot be applied in that reaction, we can use potentiometric method to detect the endpoint. And it is a physicochemical method because we are using some instrumental thing to detect the endpoint. For colored solutions or for very dilute solutions, we can use this potentiometric method for endpoint detection in the redox reaction. Some common oxidants and reductants. So oxidizing agents are mentioned here: potassium permanganate, potassium dichromate, potassium iodate, potassium bromate, ferric sulfate, iodine, lead dioxide, and potassium periodate. Reducing agents: ferrous sulfate, sodium thiosulfate, stannous chloride, oxalic acid, titanous sulfate, and sodium arsenite. Amongst these, potassium iodate, bromate, dichromate, biiodate, iodine, arsenous oxide, and sodium oxalate can be used as a primary standard. Hence, their standard solutions can be prepared by direct method. So, out of these oxidizing agents, these and reducing agents, these are your standard primary standards. Okay, because we can directly prepare their solutions without standardizing. Okay, this is also very important. Like their question can come in GPAT, like which of the following is a oxidizing agent, which is also can be used as a primary standard. So you need to know that potassium iodate, bromate, dichromate, and biiodate are the oxidizing agent which can be used as primary standard, and your arsenous oxide, sodium oxalate. Okay, these are your reducing agents which you can use as a primary standard. Next, we are going to study iodometry and iodimetry and iodometry. Okay, these are two different spellings and two different things. Iodimetry and iodometry. Okay, we will clear that as well. What is the difference? Iodimetry and iodometry. Iodine can be very conveniently and accurately titrated with standard thiosulfate solution. Okay, with standard thiosulfate solution, we can what we can do, we can accurately titrate. Okay, iodine. Two types of iodine titrations are possible. First is iodimetry and next is iodometry. So iodimetry, standard iodine solution is used, and the liberated iodine during chemical reaction is titrated. Okay, so what is the difference between iodimetry and iodometry? I will tell you. Ekdam easy language mein I will tell you. Iodimetry means in which we are using standard iodine solution. Okay, and iodometry in which we are conducting a reaction, and after the reaction is conducted, iodine is liberated or is a product or byproduct, and that iodine we are using as a titration. So that is the iodometry. Okay. Next is gravimetric analysis. So iodometry, iodimetry, only we had studied the concept. That is not much important for your GPAT. Only concept should be clear. Next is gravimetric analysis. This also we'll be seeing in short. Okay. So in gravimetric analysis, first is the precipitation techniques. Okay. Gravimetry also uh, or gravimetric analysis or titration also involves formation of precipitate. Okay, so precipitation method is a process of weighing an element in the form of precipitate which was separated by filtration from solution. So here what we do in gravimetric analysis, basically what we do, we weigh the precipitate, okay, the amount of precipitate that we get from the reaction, we weigh it, okay. Factors affecting on precipitation method: precipitate must be free from soluble impurities, precipitate must be insoluble in solution, precipitate must be readily separated from the solution by filtration, and precipitate must be convertible into a pure compound by ignition or by pure or by simple evaporation. So these are the basic requirements for a precipitate to be formed, okay. Example of gravimetric analysis of sulfate and halide is given, okay. So AgCl and BaSO4 precipitate is forming here. The colloidal state. So what is the colloidal state? We get colloids are mixture of solvent and suspended particles, okay. So particles are very too small to see, but they are larger than molecules. Due to their small size, they do not settle out of solution. There are several types of colloids like aerosol, foam, emulsion, solution, solid foam, solid emulsion, solid solution, and their examples are given here. Okay. Why we are studying colloidal state? Because in gravimetry, before formation of a precipitate, the solution gets into the colloidal state. So these are different kind of colloidal states. Then again this is in your tabular form, okay. So dispersed phase, if it is gas, and continuous phase is liquid, means gas in liquid, then we call it as a foam. Gas in solid, we call it as a foam. Liquid in gas, we call it as a aerosol. Liquid in liquid, we call it as a emulsion. Liquid in solid, we call it as a gel. Solid in gas, we call it as a aerosol, and solid in liquid as a solution, and solid in solid as a solid solution or solid mixture. So here we end with our session of all the titrations.